Okay, girls. So we're going to continue our discussion about Newton's laws and forces. This lecture, with one exception, is going to be completely conceptual. Instead of doing demonstrations of the laws here on the screen in my classroom, I'll do them with you in person on Thursday. So I'm going to kind of just like crank my way through Newton's laws, and we'll really look at some specific examples of each of those, and hopefully physically see them in class on Thursday. So before I get into Newton's laws, I want to wrap up where we were at on Monday. Monday, I classified forces in two different ways. I said they can be either internal or external, which context clues should make some sense. And in physics, we tend to really emphasize the external forces because those are the ones that are really going to change in objects' dynamics, its motion. We can also classify forces as being field or contact. And so, again, we defined this on Monday, so you should already have it in your notes. But a force is a contact force if it involves physical contact. So two objects that are touching in some way. And a force is a field force if it acts at a distance. So, as I mentioned Monday, Newton was the first person to come up with field force. Gravity was the first of the many field forces that was explored. And it was an idea that was not accepted for many years because it sort of felt like magic, right? The idea of forces or interactions happening at great distances didn't seem to make sense in those early days of physics. But as it turns out, field forces, even though we're not going to be working with them much at all in this particular chapter, really in this semester, gravity and electricity, we'll sort of dabble with it. But field forces are fundamental to our understanding of the universe. So much so that we say that there are four fundamental forces of nature. Some argue that there might be a fifth. We'll see what happens with that idea in the next decade or so. But we now would say that there are four fundamental forces in nature, and all four of those fundamental forces are field forces, so they all act at a distance. And those four forces, I just want to kind of list what they are and briefly talk about what they do. I'm not going to give a good explanation. Are the strong and the weak nuclear force. So you have it in front of you in the notes, so I'm just going to write weak. So the strong nuclear force, the weak nuclear force, the electromagnetic force. We sometimes call that electromagnetism. I can't spell. And then the last one is gravity. The final of those forces is gravity. And when I listed them, and you have these again in your guided notes, but when I listed them in order of decreasing strength. So the strong nuclear force is the strongest of these four fundamental forces. Gravity is actually the weakest of them. So it's the one that should feel the most familiar to us, but it's the weakest of these fundamental forces. And also, as it turns out, they're listed. So again, this is the strongest one, this is the weakest, but they're listed in order of the distances over which they can act. So they're all acting in a field at a distance. This one is over very short, and I'm talking less than atomic size distances. And gravity, as you may know, if you think about what we know about the universe, can act over incredibly long distances. So they go in order, the distance over which they can act. So again, strong nuclear force is happening within the nucleus of an atom. So that's the kind of distance we're talking about. Gravity, right now, here we are on one of those outer edges of the Milky Way from the video we saw last week. We are certainly being greatly influenced by what's happening in the center of our Milky Way, which is millions and millions and millions and millions, really billions and billions and billions of miles away from us, okay? So a huge shift in these distances. So just to give a brief synopsis of what these are, the strong and weak nuclear force are fundamental forces because they're fundamental to how an atom's structure is, how an atom is structured. So I don't know if you've ever thought to yourself, like if we think about the nucleus of an atom, the nucleus of an atom contains two things, right? It contains protons and neutrons. Neutrons have a neutral charge, protons have a positive charge. And somewhere, probably before I'm telling you this right now, you've heard that in electricity, like charges repel. and opposite charges attract. So that means if I have a positive and a negative charge, they're going to attract to each other, and if I have two negative charges, they're going to repel, right? Or two positive charges, they're going to repel. So again, let's go back to the nucleus of the atom. The nucleus of an atom is made up of several, up to many, it depends on the atom itself, positive charges. And yet it's bound, very, very, very tightly bound, right? It takes an enormous amount of energy to break the nucleus of an atom apart. So what is it that's keeping it together? If it's actually made up of these protons that should be repelling each other, there's got to be some force stronger than electricity that is keeping the nucleus together. And so I'm not going to explain exactly how these things work, but that's the strong and the weak nuclear force. So they're fundamental, like I said, in how an atom stays together. The electromagnetic force is the force that we see when we're dealing with electricity and magnetism. That's really all I'm going to say about it right now, because we will get into this later in this course. And then gravity is a force between masses, and it acts at a distance. This is fundamental to our understanding of like space, the universe, what space is really. Space is bends in gravity, or bends in space caused by mass. So our understanding of the universe, it hangs on gravity. Understanding of atoms hangs on this. Electromagnetic force all around us. Light, right, behaves as an electromagnetic wave. So there's a lot you can do with this one as well. So anyways, those are the four fundamental forces, some of the most important forces we have in all of physics. All four of them are field forces, as I said, and we're really not going to work with them much in this chapter, minus gravity. So what we're going to do is jump into the forces that are a little bit easier to picture. These are quite abstract, right? This is a little bit more modern physics. So we're going to jump into the forces that are a little bit easier to picture, and they were first proposed, several hundred years ago, and an understanding of Newton's laws of motion will allow us to work with those forces. So let's start with Newton's first law of motion. Oh my, this board's a mess. Okay, Newton's first law of motion states, it's written many different ways. I'll say it the way that I think you've heard it before, so it sounds a little bit familiar. So the way I think you've heard it is something like, an object that is in motion will stay in motion, and an object that is at rest will stay at rest unless acted upon by an outside unbalanced force, or you could say external unbalanced force. So again, I'll repeat it. Hopefully you can just pause and write things down since you're stuck with a recording of me. But I'll repeat it one more time. An object in motion will stay in motion, and an object at rest will stay at rest unless acted upon by an external unbalanced force. Okay? So this was a big deal at the time. This goes directly against Aristotle's view of motion that I was discussing a couple of days ago in class. So Newton says an object at rest will stay at rest. Okay, that seems to make sense. If I have something sitting on a table or a desk or even here on the board, here's my eraser, it's sitting there, right? It's going to, so the object is at rest, it's going to stay at rest unless it is acted upon by an external unbalanced force. Here I am, external unbalanced force, boom, there's a change, right? There's some motion. So that makes sense. That's pretty intuitive. This other part of the law is the part that goes against what Aristotle would have said. So Newton says an object in motion will stay in motion. Aristotle would have said an object in motion is going to come to rest. Its natural state is to be at rest. Everything stops. Newton says no. I propose, an object that is in motion will stay in motion unless it's acted upon by an external unbalanced force. Now, we know Newton's right. Aristotle is describing what we see here on Earth all the time, right? If I push this, no matter how hard I push, it's going to stop eventually. On Earth, we don't see what we would call perpetual motion. So if I start swinging a pendulum, eventually it slows down and it stops. If I kick a ball, it stops somewhere, right? You don't see it just keep on going forever. But we now know the reason that object that's in motion stops is because it's acted upon by an external unbalanced force. We usually call that force friction. So Newton was right. An object in motion will stay in motion unless it's acted upon by that external unbalanced force. And places where you can achieve a frictionless environment, we see objects continue to be in motion. So that is Newton's first law of motion in a nutshell. Sorry, I'm just grabbing the PowerPoint so I follow the order. The other term that I threw out there was inertia. So this is sometimes called, Newton's first law is sometimes called the law of inertia. So inertia is a term that means an object's resistance to changes in motion. An object's resistance to changes in motion. So inertia is equal to resistance to changes in motion. So if you think about something, you can think about it two ways. If something's at rest and you want to get it moving, the more difficult that is, the more inertia we would say it has. Or if something's already moving and you want to change its motion, let's say you want to change its direction or you want to stop it, again, the more difficult that is, the more inertia it has. So we have to think about, well, what factors impact inertia? You could, so hopefully you're pausing, think about that. What factors would contribute to this? There are two that come to mind, but one that is most discussed, and that is mass. So you've had mass described or defined as the amount of matter that an object has, which is correct. But some people would say, oh, it's the amount of inertia something has. So if something is really, really massive, it has a whole lot of mass, it's going to have a lot of inertia. So stating the obvious, if I had two balls sitting here on the floor in my classroom, if I had a soccer ball and a bowling ball, and I wanted to get both of them to move, clearly the soccer ball is a little bit easier, right? And the reason that it's not resisting the motion so much is because it has a lot of mass. So mass is directly proportional to inertia. The other factor that can impact how much inertia something has is its velocity. So even a very small thing, if moving very quickly, right, with a whole lot of velocity, can be difficult to stop or turn. So that can also impact something's inertia. Sorry, I just want to follow my order. So when we're studying mass, which again is tied to inertia for us, so it tells us how something resists changes in motion. Just like your previous science courses, when we're measuring mass, we like to measure that in the SI unit of kilogram. So we're going to start to see that come up in problems. We have to use this mass a lot, and it's going to be measured in kilograms. We will talk more about this Thursday because I think it can be confusing, even though I don't think this will be the first time you've heard it, but I want to be in person for it. There is a difference between mass and weight, right? You hear that they're different, and you've probably learned before, maybe not, that one can change and the other can't. Sometimes some people will say that. It's not quite true, but mass is a property of the object itself. Weight is a property of sort of the environment the object is in, okay? So I have a certain mass because this is my body, and I eat what I eat, and I have had kids, and I exercise where I don't, and I have my genetic structure, so this is me, and I have a certain mass in kilograms. It's again, the measure of the amount of matter that my body has. Weight would be the environment I'm in. So because I'm on Earth, I have a certain weight. If you take me and you put me on the moon, my weight is going to change pretty dramatically, actually, but it'll look the same, right? So I have the same amount of matter, is what I'm saying. You haven't taken matter away from me by doing that. So again, we'll get into like the actual calculated difference and how you could find one or the other on Thursday. But mass, the important thing to know right now is that that's a property of the body itself, not the environment. It isn't. So if you take me and you put me here on Earth or on the moon or in the sun somehow in a survivable way, or just out in a spaceship, I'm going to have the same mass in all of those places. Okay, so that is the first law in a nutshell. Newton's second law of motion. So I'm skipping a slide where it has some of the applications because I want to show you that on Thursday. So Newton's second law of motion. again, this law as well, there's multiple ways of stating this law, particularly this one. Because this is the law that's going to appear to us in equation form. So there's a couple different equations that state Newton's second law. We're going to start with the one that we're going to use, and also it's the one I think you've seen before. So Newton's second law, he is looking at the relationship between three different variables. He's looking at the relationship between force, which we'll indicate with an F, mass, which will give the M, and acceleration, how an object's motion would change, which we will indicate with an A. Okay, so he is looking to build a relationship with these three things. And so what he does is he looks specifically at how force impacts acceleration and how mass impacts acceleration. And it sort of starts as a thought experiment. It was experimentally proven as well. So let's start first with force and acceleration. So if we're going to look at the relationship between force and acceleration, we need to keep the mass constant. So I'm going to set it up as a thought experiment. We'll actually look at some demos on Thursday. So I'm going to apply I'm going to have two identical masses. So let's stick with kicking balls since I was talking about that previously. So I have two identical soccer balls side by side. And I am going to apply different forces to those same masses to see what the relationship is between the force applied and the acceleration of the ball. Okay? So I could come up to one, and you can imagine, you know exactly what's going to happen. I come up to one and I tap it with my foot, just a light little kick, tiny little kick. And then the ball right next to it, again, identical mass. I'm going to kick it as hard as I can and make solid contact with the ball. So one could say, how will the accelerations compare? And as I'm sure you are guessing along with me, we would say as the force increases, so the force on the soccer ball goes up, the acceleration is going to increase as well, right? So we say that force and acceleration have a direct relationship. So if we write that down, I don't know how well you can see this because this marker is terrible. I'm going to get a blue marker. Okay. This is bothering me because it doesn't match. But we would say force is directly proportional. That's what this little symbol means. So it looks like a fish, kind of. Force is directly proportional to acceleration. As one goes up, the other will go up as well. And then Newton kind of applies the same thought experiment to look at the difference between mass and acceleration. So let's go back to that soccer ball, bowling ball example I discussed earlier. If I have these two side by side, so I have two different masses, and I'm going to apply the same force to each of the balls. So I'm going to go just kind of kick each one. Which one will have the higher acceleration? So if we think about this, if I have a soccer ball and a bowling ball, and I come and kick each of them with equal kicks, clearly the soccer ball is going to go further, it's going to have a larger acceleration, right? So what we see here is that mass and acceleration have what we call an inverse relationship. You can write as 1 over m is proportional to a, or m is proportional to 1 over a, it doesn't matter. And so as m goes up, a will go down, and vice versa. As this goes down, this will go up. So this is an inverse relationship. Now, if we put these relationships together, which again, you can only put them together and make them an equation if you use some kind of experiment to prove this. You could say f over m is equal to a, and we rewrite that as f equals m times a. So this is probably the way you've seen it before. Now, I'm going to add one symbol to this equation and write it in its true form, and this symbol is what gives us all of our trouble in this chapter. And that is this symbol. Probably you've seen it before in your math class. Maybe not if you're in Algebra 2 this year. This is sigma, it's a Greek letter. And so what this means is the sum of all of the forces. So right now I was talking about kick, and that's really just one force acting on the ball, right? But a lot of times there are multiple forces acting on an object, causing it to accelerate or decelerate. So we need to look at all of those forces acting on the body because they're all impacting its motion. So we say the sum of all forces is equal to an object's mass times its acceleration. Now, this is our one new equation for the chapter, really. And it seems like such a simple equation. And yet, you can do some really, really complicated things with this thing, right? One thing that we see coming out of it right away, so I mentioned it's going to be a conceptual lecture, so I'm not going to really get into the math. One thing that we see coming out of it right away is if we take that equation, F equals m times a, we kind of get a new unit here. So m is in kilograms, that's how we like that. And A, acceleration, we've seen it in meters per second squared. So kilograms times meters per second squared, this is the unit for force. We use force so often, we rename that unit just out of basically a spirit of laziness. We don't want to write that all the time. So we call that a Newton. So 1 Newton of force, the measurement of force, is a kilogram times a meter per second squared. So you'll see this unit, the Newton, by all of our forces to indicate their strength. Okay, I am going to skip the chapter, or the problem that says example 1, plug and chug. And again, we'll do that together on Thursday when we talk about the different types of problems. So let's jump right into the third law of motion. Okay, so the third law of motion, I'm going back to black because I can't stand different colors. Let's see if you can see it. Newton's third law. Okay, Newton's third law of motion states that for every action force, there is an equal but opposite reaction force. You call these force pairs. So I'll just say it's all about force pairs. Okay, so I'll restate it one more time so you can get it in your notes. For every action force, there is an equal but opposite reaction force. So right now, and again, that action and reaction force we call a force pair. Right now you can't see it because of the way the camera is oriented, but I'm sure you could guess I'm standing on the ground. I'm not floating, I'm not sinking, I'm standing on the floor in my classroom in the basement of the South Hall at St. Ursula. And so here I am, and so we say there's all kinds of force pairs going on right now, but one would be that I'm standing on the floor, so my weight is pushing down on the floor. I'm applying a force down to the floor. We could call that the action force. And the floor is pushing back up on me. That's what's keeping me here on the surface, right? And so we can call that the reaction force. Again, it doesn't matter which one's action or reaction. The point is that they're equal in magnitude and opposite in direction. Equal in magnitude but opposite in direction. Okay, so these action-reaction forces, these force pairs are always, without exception, always acting on two different objects. So I'm pushing on the floor is pushing back on me. Our two objects are me and floor. One force is on me, one force is on the floor. If I come and just lean, this is an amazing demonstration, I'm just leaning on my board while I chit chat to this camera with an empty room. I know you're thrilled. My hand is pushing in on this board, the dry erase board. The board's pushing back on me. Again, two objects, me, board. Two different forces, me pushing in, board pushing out. They're equal but opposite, right? So force pairs, again, so force pairs are acting on two different objects and they're in opposite directions. You can see these things sort of do some dramatic things sometimes. So we'll watch a video on Thursday about baseball, because I love baseball, it's postseason time. So we'll look at what happens when the bat and the ball have collisions. Maybe you've seen some of these slow-mo things with like golf balls. It's like super dramatic, but really anything that involves hard contact with the ball. You can see some crazy things with Newton's third law. One of the most dramatic examples I can think of is if you've ever had the exciting experience of seeing a rocket launch, like a real rocket. So, I mean, that's pretty complex stuff, but at its most basic, it's just Newton's third law. So there's a whole lot being expelled down from the rocket, right? And then there's a push back up from that, right? So that is Newton's third law of motion. And then the last thing I want to talk about are just some of the standard contact forces that we are going to see most often. So there's a list of forces on your slide. They are certainly not the only forces that exist by any means, but they're the ones that we're going to work with most often. So let's just kind of go through those, and I'm going to briefly define them so we can jump right into them Thursday. And that will be the end of this lecture. Okay, so the first one is the force of gravity. And of all of these forces, so this is the only field force on my list here. It's acting at a distance. The force of gravity for our problems is going to come from the Earth. The Earth will be pulling down on us. And the force of gravity is the only of these forces that is in every single problem we do. You can't escape it. So the other ones, depending on the situation, you may or may not have them there. Force of gravity is in every single thing, or every single problem that we do, because we're always going to be working with objects with mass. Now, when it comes to notation, in physics, we're pretty loose with notation, which is an object of, or a point of contention with some other field sometimes. But in physics, just generally, it's like whatever. When you're labeling your forces, because we're going to get into diagramming these on Thursday in class, when you're labeling your forces, you just need to do so consistently and in a way that the reader, so in this case the reader is me, can follow your work. So you don't have to use the notation I do. You might see different notation in college, or slightly different. But you may need to make sure that you're consistent and that it makes some sense, okay? So the force of gravity, I a lot of times, so I do F sub G, kind of like a little g for force of gravity. Or sometimes you'll see it, actually more often than not as we get going, you'll see me write as mg, which is the equation for it, which I'll explain Thursday, so not yet. So those are two ways that I diagram it and label it. But again, it's just it's a force from the earth, we'll say, for these problems. It can be from other objects with mass. And so in our case, the force of gravity is always going to be directed straight down. The earth is pulling you down towards its core, towards its center point. And so the force of gravity, assuming we're on the Earth's surface or just maybe a little bit below it or above it, is going to be straight down. The next force is on the list is the normal force. And as we go, all of these I will describe better as we get into certain situations with them, but just a brief explanation of normal force. This is present when an object is on a surface. So you have to be on a surface for the normal force to be present. A normal force is directed perpendicular to the surface. So if you're on a surface and the surface is pushing back up on you or on an object, that's the normal force. When I say perpendicular, right now I'm standing again on the floor that you can't see, but I'm standing on the floor is pushing up on me perpendicular to the surface of the floor, straight up. Or we could say this eraser. The ledge is pushing straight up. But if I gave it some angle, if I said, okay, I have a meter stick, which is a surface, and I'll just drop this list, and I'm going to put an eraser on it, friction's holding it so it's not sliding down. The meter stick is pushing up on the eraser perpendicular to the surface. That's not straight up, right? It's like kind of at an angle because this surface is at an angle. I'm changing the angle as I go here, right? So right at this moment, this would be the normal force, kind of directed at an angle slightly. Oh, and now it's sliding. Okay, so normal force only happens when something's on a surface. If something's in the air, let's say it's falling or it's hanging or something like that, it does not have a normal force. You have to be on a solid surface for this force to be present. Then I gave a general, my notation, you'll see me call like Fn. Sometimes you have multiple normal forces, so I'll call them like 1, 2, or 3, or A, B, C, whatever you want to do. But F sub n is how I label them. The next one is sort of a general applied force. Applied force are like pushes and pulls. So I usually say, some people say FAP, I usually say FP. But if you're pulling a wagon, if you're pushing a mass up an incline, all those things, those are applied forces, right? I'm coming in and I'm doing something to it. So that's my applied force. Force of friction is something we will spend quite some time on because there's different types of friction. But friction is a force that opposes motion. So it's always going to be in the opposite direction of motion. And so I indicate that typically with just a little FFR when I'm writing friction. Again, you could write the different types if you wanted. And then the last one I have on that list that we will see a lot of is tension. Really, tension's kind of like an applied force. So if you give it this notation, it's fine as long as you put it in the right spot. I call it FT instead of FP. And tension happens anytime you have like a rope or a string or maybe a spring pulling on something. So if you were in my classroom, actually, let's see if I can get on camera. It's gonna be a little wild. There's pigs hanging from the ceiling in my classroom. See this pig up there? Okay. So there's a string that is attached to the ceiling, and the pig is hanging from it because I use that pig in experiments. And I suppose I'll have to move it upstairs. And so I would call the string pulling up on the pig tension. Again, you could say, well, that's just an applied force. It's a string pulling up. That's fine too. The point is there's a force up on the pig, keeping it from falling down, and that force, because it's via a string, is often called tension. Okay. All right. So those are the common forces. Newton's 3 laws in a nutshell. Hopefully you know about the fundamental forces of nature. There's 4 of them right now. Again, maybe a 5th. We'll see. When we get into this in class, I'm just going to kind of jump into some physical demonstrations and how we can start to diagram and calculate with these things. So I will stop for now and see you on Thursday.